Okay, today we will do some problems uh, in span set. Okay, so first we discuss this problem. Okay, uh, consider VR. Sphere. VR means, right? VR means set of all polynomials. Set of all polynomials. Okay, set of all polynomials. Prove that the span of 1x squared, right, 1x squared span of, right, span of 1 plus x 1 plus s squared 1 plus x 1 plus s squared, this one equal again span of x, right, x 1 plus x 1 x plus s squared 1 plus s squared 1 plus x plus s squared 1 plus s squared. Okay, it is your question now. So how we can do this problem? Okay, so let you take one of the element this span set. Then we can write v this v one of the element of the span set. No, then we can write v is a linear combination of these vectors: alpha times 1, beta times x, gamma times s squared. Okay, alpha times x, alpha times 1, right, alpha times 1. So can write v equal to alpha times 1, beta times x, and gamma times s squared, right? So um, you know, you want to show that, right? You know, right? What is your claim now? First, what is your claim now? You want to show that, right? This one, no? You want to show that this span of 1x squared subset of the span of 1 1 plus x 1 plus s squared. Okay, So similarly, the reverse part, this one, span of 1 plus x 1 plus s squared, subset of span of 1 x squared. Okay, these two things you want to prove it. Okay, first you want to prove this statement first. Next you can consider this one. Okay, right. Now we take B belong to the span of set. Then you want to prove it, this B belong to this set. Okay, so what is the idea first? You know, we can write, right? We can write this vector equal, this vector equal A times, right? A times this vector. It is the idea, right? You can first you get the idea, then B times 1 plus x c times 1 plus s squared, right? Now what is your claim now? You want to you want to get the ABC values, right, in terms of alpha, beta, gamma values, right? Got the point now? You want to get the ABC values in terms of alpha, beta, gamma values, because you know we belong to span of this one means you can write the linear combination of vectors. Here alpha, beta, gamma belong to real numbers. Real numbers, right? You assume that we can write this b vector, right, in terms of this vector also. You assume that we can write b one of the vector, no, that one of the vector b can write in terms of this vector also. So you won't write in terms of that vector means you want to find the scalars. Okay, right? The scalar mean you want to find a, b, c in terms of alpha, beta, gamma. Okay, now you got the idea, right? Now everything is easy, right? First you can right? You can equating the components. First alpha. Here the coefficients of 1 here a, here b, here c. Next coefficients of x, beta, here b, here there's no b terms, no here. What about the gamma? Squared coefficients here, squared here only c. Okay, squared c. Okay, right now. Okay, now I already told you, you want to write, right? B equal to this one equal to this one. Therefore, B equal, what is your A now? How can you get A values? A equal to alpha minus B plus C. B plus C means beta minus gamma. Therefore, alpha minus beta plus gamma. It is your A times is 1 plus, what is your B? B is beta. What is your vector? 1 plus x. What is gamma? C is gamma, no? Gamma. What is your vector? 1 plus s squared. Now we write, right? We write B vector, right? B vector linear combination of these vectors. 1 and 1 plus x, 1 plus s squared. Therefore, this is belong to span of 1, 1 plus x, 1 plus s squared. Is it okay? Right, sorry. You can put outside span. Okay, right. This set. So this B belong to this one. Now you prove it. B belong to this one. Therefore, the span of 1 x s squared subset of span of 1 1 plus x 1 plus s squared. Okay, right. It is first one. Next, you want to prove the reverse part. That means you want to prove it this one subset of this one. So The same idea, right? Same idea. Let you take again one of the vector W, no problem, W. W belong to this span set. So 1 plus X, 1 plus S squared. So W we can write linear combination of these vectors. Okay. W we can write linear combination of that vector. So what is the idea? Alpha times 1, beta times 1 plus X, gamma times 1 plus S squared. Okay, right. What is the idea now? Now W belong to that span set means we can write W is this is a linear combination of vectors, right? Now we want to write the linear combination of vectors, right? We want to write W as a linear combination for these vectors. Which one? 1 X S squared. So you put A times 1, B times X, C times S squared. Okay. So now your claim is you want to find A, B, C values in terms of alpha, beta, gamma. So I think like this. Okay. So first equating the components first. So component of vector 1 here alpha plus beta plus gamma. Coefficient is A. For X components here beta, then that part B. For a S squared component is gamma, here S squared is C. So we found A, B, C values, right? Right. So right now you got the point. Now what we do? Now you can write, right? This one, right? This one equal A is means alpha plus beta plus gamma. You can write alpha plus beta plus gamma into 1 plus B is beta, C is gamma. So it is the linear combination of vectors, therefore belong to the span set 1 X S squared. Okay. We assume that W belong to this span set. We prove it W belong to this span set. Therefore, this span set subset of this span set. Therefore, this span set 1 plus X 1 plus S squared subset of 1 X S squared. It is your second condition. Therefore, 1 and 2 implies both are equal. That is your first claim. First, your claim is this one. Okay, right. Therefore, your conclusion is, therefore, span set 1 X S squared equal span set 1 plus X 1 plus S squared. So now we prove the first claim. Second claim is now, okay. Second claim is now, there are 3 numbers. You suppose you have A equal B equal C. If you want to show that A equal B equal C means, first you want to show that A equal B. We saw 2 things is enough. A equal B and B equal C, therefore A equal to C. Okay. Suppose you have 3 conditions here, A equal to B equal to C. You asked to show it's an equal, 3 terms are equal. Then you want to show that A equal to B. Next, you want to show that B equal to C. Therefore, the conclusion is A equal to C. Therefore, A equal to B equal to C. Okay. So your next claim is you want to show that, right? You want to show that, right? B equal to C. Okay. Then suppose A equal to B and B equal to C, then A equal to C. Right. This part you don't need to prove. To prove this one is enough to say A equal to C. So next we prove that one. So let B belong to this span set of which one? Now we want to prove this to this one. No, this one equal to this one. 1 plus x 1 plus s squared. So right, what is the next step now? So we can write the vector V linear combination of vectors. So V equal to alpha times 1 beta times 1 plus x gamma times 1 plus s squared. Now you can write these vectors in terms of this vector, right, using the scalars a times 1 plus x, b times x plus s squared, c times 1 plus s squared. So now your claim is you want to find the, right, you want to find the ABC values in terms of alpha, beta, gamma, right? ABC values in terms of alpha, beta, gamma. For that, you can equate in the coefficients. So for the one's coefficient is alpha plus beta plus gamma equal to A plus C. So next, our x coefficient is beta only. A plus B. Then S squared coefficient is gamma. B plus C. Is it okay? So now your claim is you want to find ABC values from using these three equations. That is easy, no? So right. So if you add three equation, right? If you add three equation, what do you get? Otherwise, you subtract a plus c. Yeah. So if you subtract, very easy, you know. You can put the numbers here 1, 2, 3. Just simplification. Okay. Claim is you want to find ABC values here. You can use any method. Okay, write first 1 minus 2. This give C minus B. That side alpha beta is cancelled, then alpha plus gamma. Next B plus C, you have this equation, right? You can put this equation is 1, 2, 3, 4. So now you can add to 3, 4, 3, 4 plus 3. Then you get here minus B plus B cancel C, 2C. 2C equal alpha plus gamma, no? 2 gamma. So your C is alpha plus 2 gamma by 2. Therefore, what is B? Right. What is B? So yeah, you put these values in any equation, this one or this one, then you can get the B values, no? Because you can put these values, right? C values in this equation, you get A values first. So A values is alpha plus beta plus gamma minus alpha minus 2 gamma by 2. So it is A equal 2 alpha, therefore alpha, 2 beta, 2 gamma plus 2 gamma minus 2 gamma 0, therefore by 2. So what are B values? You can put this A values, sorry, C values here. Then you get the B values. Gamma minus C values alpha minus 2 gamma by 2. So 2 gamma is cancelled. What about B values? 2 gamma is cancelled. Therefore minus alpha by 2. No? Minus alpha by 2. It is B. Now we found the ABC values in terms of alpha, beta, and gamma. So we can write this equation. You can put the star here because identify this equation. You can put Roman, right? Numbers 1 from this one equation number 1. We can write B, no? B. You can say this one now. B equal to this one now. You put A is this one. A is alpha plus 2 beta by 2. A times which one? A times the vector is 1 plus x, no? Yeah. 1 plus x. B plus alpha minus 2 gamma by 2. Alpha minus 2 gamma by 2 is one of the scalar. Alpha minus 2 gamma by 2. Sorry. What is B? This one. Minus alpha by 2. What is the vector? X plus x squared plus what is A, B, C? C is alpha plus 2 gamma by 2. Here 1 plus s squared. So this is linear combination of vectors, no? Therefore 1 plus x, x plus s squared, right? X plus s squared, 1 plus s squared. Okay. Therefore, right? Therefore, we assume that B belong to this span set. Now we prove B belong to this span set. Therefore, the span set 1 plus x 1 plus s squared, the span set subset of this span set. 1 plus x plus s squared, 1 plus s squared. Okay, it is your first, right, part proof, right? For next, you want to show that this is subset of this one, right? This span set subset of this span set. So you want to show that one, right? You want to show that one. You take the element, right, from this set, right? For that, let W belong to this set. So we can write linear combination of this vector as a alpha times 1 plus x, beta times x plus s squared, gamma times 1 plus x squared. Those. So it is equal, right? You want to show that W belong to this span set, no? So A times 1, B times 1 plus x, C times 1 plus s squared. Now your claim is you want to find ABC values. So first equating the coefficients. So alpha plus gamma, alpha plus gamma, A plus B plus C. So next, quotient of X, therefore alpha, beta. Quotients of X here, B only. Now quotients of X again, sorry, X squared, beta plus gamma. Quotients of S squared again, C. Okay, C. Now you want to find ABC values in terms of alpha, beta, gamma. Okay. ABC values in terms of alpha, beta, gamma. So so if you add, what about A values? A values means, right? If you add these two equations, subtract here, because here B plus C values there, then you put here B plus C values and you can get A values in terms of alpha, beta. So your A is alpha plus gamma minus B plus C. So B plus C, what is the B plus C values? You know B plus C values, then you can easily find the alpha A values. B plus C is alpha 2 beta plus gamma. Alpha 2 beta plus gamma. So it is alpha cancel minus gamma minus gamma also cancel, minus 2 beta. Okay, right. What about the BC values is no, because we want to find ABC values in terms of alpha, beta, gamma. B values, you know that alpha plus beta. C values also you know that beta plus gamma. You don't need to find that values because you already know that, in terms of alpha, beta, gamma. So now W, okay, W, you can say this one now. This one equal to this one. What about A values? A values is this one. Minus 2 beta. Vector is 1. Plus, what about the B values? B is this one. Alpha plus beta. What is the vector is 1 plus x. What about this C values? Beta plus gamma. Vector is 1 plus s squared. So this is linear combination of vectors of this one. 1 plus x, 1 plus s squared. So we assume that W belongs to this span set. Now we prove this W belongs to this span set. Therefore, right, therefore 1 plus x, x plus s squared, one plus s squared subset of 1 plus x, 1 plus s squared. So it is second one. We already proved first one. This is the second one. Therefore 1 and 2 implies both are equal. That means this one equal to this one. This span set 1 plus x, 1 plus s squared equal 1 x plus, sorry, 1, no, there's no 1, which value is 1 plus x. Yeah, 1 plus x, x plus s squared, 1 plus s squared. So now we prove this one equal to this one. Therefore, 3 span sets are equal. Therefore, our last conclusion is 3 span sets are equal, because we already proved this span set equal to this span set. Now we prove this span set equal to this span set. Therefore, conclusion is this span set equal to this span set equal to this span set. Oh, this is your last answer. This is all three terms, all three span sets are equal, right? Because this one equal to this one and this one equal to this one. Okay, therefore, span set 1x squared equal span set 1 plus x 1 plus squared equal span set 1 plus x plus squared 1 plus squared. Okay. Okay, right. Okay. Next question is, right? Okay, next question. Okay. Suppose that right, suppose that a set of vectors, right, s here v1 v2 v3 and v4 Okay, v1, v2, v3, v3 is a spanning set of subspace B. I think here v3, right? It is v3 is a spanning, right? It's a spanning, right? It's a spanning set of a subspace B, spanning set of a subspace B, right? Spanning set of a subspace B, right? B subspace B in R power 5. Okay. These are the span vectors of S. S is a subspace of B in R5. Okay. It's V1. Is R5. Okay. R5. Right. Okay. Now, suppose that a set of vectors, this one v1, v2, v3 is a spanning set of a subspace of B in R5. You add another vector, right? Here we add if B4 is another vector in B, if B4, right? If add another vector, B4 is another vector in B, B4 is another vector in B, right? Then, right? Right. Another vector in B, right? Then is the set, question is, then is the set S2, you can put here 1, S2, V1, V2, V3, you can add V4. Still, right? V2, that means S1, V1, V2, V3, V4, still a spanning set for V. Still, they are still a spanning set for V. They are already, S1 is a spanning set for V. Now they ask if you add another vector V4, still this S2 is also span set for V or not. Okay, span set for V or not. Okay, if so, prove that. Otherwise, give the counter example. If so, prove that. Okay, if so, prove that. Otherwise, counter example. So you want to give the examples. Okay, right? So you want to give the examples. It is false, you want to give the example. It is true, then you want to prove that this condition. You have S1, V1, V2, V3 span vectors. If you add another vector V4, again, still span set, satisfying conditions. Okay. So, you know, S1, V1, V2, V3 spanning set means you can write linear combination of vectors V1, V2, V3. If you add V4 vector, Then on after that also you can write this v1, v2, v3, v4 vectors as a linear combination of vectors. Okay, right. Okay, so how can you prove this one? So first you want to show that S2 is the right. You want to show that S2 is the still spanning set for V or not. Okay. Right. Let belong to let X belong to span of X2. Then you can write X is a linear combination of vectors. You can put C1, V1, C2, V2 for S2, no? C3, V3, C4, V4. Okay, C4, V4. Where C1, C2, C3, C4 are scalars. Now, here given condition is S1 satisfy the span condition. We have, right? We have, right? We have fan of S1 equal V. We have fan of S1 equal to V. So, right? So, fan of S1 equal to V mean you can say this one up to this one, right? C1 V1 plus C2 V2, C3 V3, right? Right? C1 V1, C2 V2, and C3 V3. So that means C1 V1, C2 V2, C3 V3 is a vector of B, right? Vector of B, because this is the span set of S1 is equal to B, no? It's a vector of B. Using the, similarly, C4 B4 is a vector in B, because B4 one of the vector in B, C4 scalar, this closure property of the vector scalar multiplication for a vector space, you can tell C4 B4 is a C4 B4 belong to V. Therefore, you in the addition, you can add this two closure property C1 B1, C2 V2, C3 V3, C4 V4 belong to B. It is right, right? C4 B4 belong to B, right? That means you assume that X belong to span of X2. Now we prove this is your X, no? X belong to B. Therefore, span of X2 subset of B. Span of S2 subset of B. Right? Next, you want to show that B subset of fan of X. Next, your claim is B subset of fan of S2. Still, they ask here, suppose that a set of vectors S1 is a spanning set of a subspace B in R5. If B4 is another vector in V, then it's a set S2 still a spanning set for V. That means span of X equal to, yeah, span of S1 equal to V. Now you want to show that fan of S2 also equal to V. So for remaining, you want this, show this claim. Let you take one of the element B belong to B, right? But B already we know that B equal to fan of S1. It is given one. Okay, B equal to span of X1. Therefore, you can write B in the vector B linear combination of vectors, right? That means you can take C1, C2, C3 belong to real number such that B equal C1 V1, C2 V2, C3 V3. Okay, C1 V1, C2 V2, C3 V3, because the spanning set consists only V1, V2, V3 vectors. Now, is it okay? B equal C1 V1, C2 V2, C3 V3, 0 times V4. 0 times V4. Now, this set belong to span of S2. This set belong to span of S2. Okay. Therefore, we assume that P belong to span of S1. Now we prove B belong to span of S2. Therefore, right? Therefore, B subset of fan of S2, right? B subset of span of S2. here, right? From this one, we prove here B belong to pan of S2. We prove because B belongs to B. Now we prove uh, B belong to pan of S2. Therefore, B subset of pan of S2. Therefore, from this one we can conclude that, right, B equal to S2, span of S2, right? B equal to span of S2. We already have B equal to span of X1. Therefore, span of S1 equal to span of S2. No, span of S1 equal to, therefore span of X1 equal to span of S2 equal to V. Okay, span of S1 equal to span of S1 equal to span of S2 equal to V. Okay. Okay. Okay, now I will stop here. Next class I will do some problems again the in pan sets.